So the first question people usually ask when they're being introduced to the idea of scintillators is why would you want to use this for radiation measurements? And there are multiple reasons, but the primary one really is that they're water equivalent for megavoltage photons and electrons. So for small fields in particular, there's a lot of difficulty in measuring these small fields because your detector perturbs the interaction of the radiation beam right there at the point of measurement, where a truly water equivalent, fully water equivalent detector doesn't perturb the measurement there. It really is invisible to the beam. Scintillators can be made very small, so you can get good fine resolution for the geometry of your measurement. They are energy independent for that megavoltage range. There's a publication about the beam quality correction factors for these scintillators showing the beam quality correction factor is unity. Again, that reflects back to that true water equivalence of the detector. There's a small temperature dependence. It's about 0.1% per degree for these the scintillator that we're using. So really you can ignore that correction if you're doing all of your measurements at room temperature. And then another advantage with some of the newer irradiators is that this can be used with MR Linux. There is no ferrous material at all in the scintillation fiber itself. As long as your electrometer stays outside the 5 Gauss line, you can use those with the MR Linux with no problem. Our scintillator that we use is an organic scintillating material coupled to a PMMA optical transfer fiber. The original device, the W1, had a 1 millimeter diameter and 3 millimeter long cylinder of that scintillating material. With the W2, we make both the 1x3 to match the W1, as well as a 1x1 millimeter scintillator. You do have to correct for the stem effect light, the Cherenkov light that is produced within that PMMA optical transfer fiber, though. That is kind of the one sticky point in using scintillators, is that there is this additional signal, visible light signal that's produced via the Cherenkov effect. So we use the 2-channel chromatic correction that's based on a publication from Matthew Guyot from 2011. That separates that light into 2 portions of the spectrum, and I'll show this on the next slide. The other difficulty with scintillators, well, not really difficulty, but thing to be aware of, is that these are not dosimeters that you can send off to the calibration lab and have them calibrated, and then they're going to be a stable measurement for the next 3 years. It is something that does degrade with dose, and therefore you have to do a cross calibration yourself to link the output of the scintillator with a known dose. So as you use the device, the signal decreases about 2% per kilogray of dose that the scintillator receives. You have to cross-calibrate it with a known beam or a reference detector in order to have output in terms of dose. This 2-channel chromatic correction from the Guyot publication splits the light into what we're calling blue and green portions of the color spectrum. Our scintillator is a blue scintillator. Cherenkov is a broad spectrum contaminant light, and therefore the summation of the spectra are shown here is shown, I guess, in the black line. With measuring those two sections of the spectrum, we can calculate a correction factor that we use to remove the Cherenkov signal by having you do a set of characterization measurements. And the idea of these characterization measurements is that we're keeping the dose to just the tip of the fiber, that active scintillator portion, we're keeping that the same, and we're changing the amount of optical fiber that's in the field. So the only thing that's changing in this spectrum plot is the magnitude of the Cherenkov signal would increase as you put more of the fiber in the field. But this scintillation signal from dose to the scintillator itself remains the same. So if you do these 2 measurements, we provide a water jig for this with the W2, where you can have the fiber coming straight out of the field for the minimum fiber configuration and then wrapped around for maximum fiber configuration. And this fits within a 10 by 10 field easily. Or there's a slab that we had originally made for the W1, and a lot of people like it for the W2 as well, that fits in a 30 by 30 field. but you would have the fiber straight out for your minimum fiber configuration and then wrapped around in this channel for the maximum fiber configuration. But after you do those two measurements, we can calculate what's called a Cherenkov light ratio, or CLR, correction factor, taking the difference in signal in the blue channel divided by the difference in signal in the green channel. And that gives us this correction factor that can be applied in subsequent measurements to tell you that the value that's coming just from the scintillator itself is that blue signal minus the green times the Cherenkov light ratio. If you give your device a dose calibration, irradiate it with a known dose and a reference field size, then we can create a dose conversion factor that really is just a multiplicative in this equation to convert the units from charge collected to dose. The original device was the W1. It's been on the market since 2014. It has, as I mentioned, that 1x3 millimeter active scintillation volume. There are numerous publications talking about the W1. The most notable recently, I guess, has been the joint publication from the AAPM and the IAEA on small field dosimetry. That's the Technical Report Series 483 publication, which lists the W2 as having that beam quality conversion or correction factor of unity for all field sizes and all beam energies that it appears in the table. And I'm happy to say it's the only one in that publication that has that claim. All of the other detectors have correction factors as that field size decreases. The difficulty with the W1, or limitations of that, is that it was designed just to be a single point measurement system. It was our first generation device. It also has the optical collection, or the optical component, directly connected to the optical fiber. And then you need a 2-channel electrometer in order to read out that blue and the green signals and perform the Cherenkov subtraction calculation. So something like our Supermax electrometer is required for use with the W1. With the W2, we took things one step farther and we made this just a user replaceable fiber. It's a standard optical connector at the end. But then we combined the optical readout with the electronic signal processing into one dedicated electrometer, which we call the Max SD. So because this is an easily swapped out fiber, it's that standard SMA connector, we have both a 1x1 millimeter scintillator option and a 1x3 millimeter option, and we have longer fibers for use with MR-Linacs. The Max SD, that dedicated optics and electronics system, will take in the optical signal, perform a fast Cherenkov correction, and then can convert that signal into a proportional analog output that's sent back to the water tank electrometer if you're doing small field scanning. This is done for every 10 millisecond integration so that your scanning can or the data can be collected with your scanning electrometer. We do provide a signal gain on that output signal so that we put the signal into a measurement range that's appropriate for a water tank. The scintillator itself creates a very small signal. So what this looks like in the water tank is that you would set up your scintillator. There's a stem adapter that we provide in order to allow you to clamp down on this in a standard chamber holder. The fiber itself is quite small, and so that it would otherwise need a dedicated holder. But the other reason for this is that then provides some extension of the fiber out in front of your scanning equipment so that you're not measuring right up there next to something that might perturb the beam as well. But that fiber then is connected to the Max SD. The output of the Max SD goes into the input of your water tank scanning electrometer. And from the standpoint of the electrometer, it looks just like a diode. It's a detector that you don't apply bias to, but as soon as the beam is on, the water tank electrometer receives a current from that measurement. We do recommend that you scan slowly with this detector. For small fields, we scanning, we recommend about a 1 second measurement for each dwell point rather than doing something like continuous scanning or short measurements. And that's really in order to make sure that the noise in your scan is lower, because this is a low signal device. The nice part about it is that you're confident that these are accurate measurements. You don't have to apply additional corrections based on the changing field size in order to account for the energy dependence and field size dependence from your detector. Just one example from the initial publication when the W2 first came out from Paulina Galavis and the group at NYU Langone. They compared W2 scanning with film measurements, and this is a 1-by-1 field that they scanned and got very good agreement between the W1 and the film. They also checked, as was checked with the W1, dose rate dependence and dose dependence, and saw, as predicted, it behaved the same way as the prior fiber constructions, exactly the same. We didn't expect that to change, but it's always nice to have confirmation. Another publication which came out of the University of Alabama at Birmingham and Richard Popple's group, this is Dr. Snyder's publication on dose measurements of variant hyperarc treatments with very small targets. They looked at dose measurements with the W2 scintillator compared with film measurements for targets down to a 3mm diameter target, and got very good agreement again between the W2 measurements and film. This is an image out of that publication showing the measurement, or the imaging for alignment and treatment planning. If you have just the W2 fiber in this chamber plug, you can't tell where the active portion of the detector is. And again, that reflects back to the water equivalence of the detector. The good thing about water equivalence is it's invisible to the beam, and the bad thing about water equivalence is it looks invisible in imaging. You can't see it. So we do provide a dummy fiber with a BB in order to allow you, or give you some assistance in trying to make your treatment plan, as well as align your phantom for some of these QA measurements. So that's actually all I had. It's a fairly short presentation today. I do appreciate that you took time out of your schedules in order to be here with me today. If you have questions, I'm happy to answer them now. You can also get information on our website, standardimaging.com, or reach out to your sales representative or distributor. I see there are some international folks on the list today, and they can assist you with some additional information as well. So thank you very much. I'll look for questions for a little bit here, but if nothing shows up, I do appreciate your time, and I hope you have a great rest of the day.